world of semiconductors. You will learn about the N materials and P materials. You will see how they are formed and how they function in solid-state devices. You will also learn about the depletion region in a semiconductor device, and you will see that by controlling the depletion region, you can control the device. Next, you will study many of the more common solid-state devices to gain a better understanding of semiconductor theory. You will see how these devices actually work. You're watching a listing of some of those devices to be covered in this video. Finally, you will see how many of today's integrated circuits are manufactured using a technique called monolithic fabrication. To gain a better understanding of semiconductor theory, we must first examine the atom. Here we see a silicon atom. As you may have noticed, the outermost ring of electrons are contained in an electrostatic force called the valence shell. In a pure silicon atom, the valence shell will contain only 4 electrons. The most electrons which may exist in the valence shell are 8. The closer the electrons are to the nucleus, the stronger the forces are that bond the two together. Therefore, each shell of electrons will have an associated energy level that will represent the amount of energy required to remove an electron from the shell. Since the electrons in the valence shell are the furthest from the nucleus, they will require the least amount of energy to become displaced from the atom. When atoms are combined to form a solid material, the electrons in the valence shell of each atom will be influenced by the forces created from the neighboring atoms. As these atoms merge, energy levels are created within the atomic structure of the material. In any given material, there are 2 distinct energy bands in which the electrons may exist. These are the valence band and the conduction band. Separating these 2 energy bands is a third band in which electrons do not normally exist. This band is termed the forbidden gap. The electrons in the conducting band are those which have been displaced from the valence band. These electrons are easily moved within the material with only small amounts of energy being applied. The electrons contained in the valence band, on the other hand, will require a much larger amount of energy to become extracted from the valence band and forced into the conduction band. Depending upon the type of material which the combined atoms form, the forbidden gap may be large, small, or non-existent. The difference between insulators, conductors, and semiconductor materials will depend upon the size of the forbidden gap within the materials. To gain a better understanding of this, we will first examine insulator materials. As you may have noticed, the insulator has a large, wide forbidden gap. Therefore, it will require large amounts of energy to displace the electrons from the valence band. For this reason, insulating materials make very poor conductors. Conductors, on the other hand, have no forbidden gap at all. The conduction and valence energy bands will actually overlap. Therefore, only small amounts of energy are required to move the valence electrons through the material. Conductors normally have very large numbers of electrons available for conduction. As you can see here, semiconductor materials have a much narrower forbidden gap than did the insulator materials just discussed. Therefore, the semiconductor material will require much less energy to extract the electrons from the valence band. But in the same respect, the semiconductor material will require more energy to displace these electrons than would be required by conductor materials. As a rule of thumb, elements with 5 or more electrons in the valence shell are considered electrical insulators. Elements with 4 electrons in the valence shell are considered intrinsic semiconductor material. And elements with 3 or less electrons in the valence shell are considered conductors. Silicon and germanium are the 2 most common semiconductor materials used in solid-state devices. The atoms contained in any solid material are held together by a force referred to as a bond. There are 3 kinds of atomic bonds. These are ionic, metallic, and covalent. Insulators are formed with ionic bonds. Insulators will contain both positive ions and negative ions, which create a strong electrostatic force of attraction between the atoms. It is this electrostatic force which bonds or holds the material together. The term ionic bond is used because the atoms are ionized. Metallic bonding occurs in materials which are used for conductors. As you learned earlier, conductors contain a large number of electrons which are available for conduction. As the electrons leave the valence ring of the atoms within the material, the atoms become positively charged and therefore become positive ions. A strong electrostatic force will exist between each atom and the many free electrons. It is this strong electrostatic force between the atoms and free electrons which forms the actual bonding of the material. Covalent bonding occurs in materials which are used for semiconductors. Covalent bonding holds the atoms much closer together than does the ionic or metallic bonds. Semiconductor materials contain both positive and negative ions. The positive ion will contain holes in which electrons could exist, while the negative ion contains extra electrons. Since the atoms are held closer together, the valence shell in each atom will share electrons with the neighboring atoms. This results in a strong covalent bonding action between the atoms. This sharing of electrons causes the atom to act as if each atom had 8 electrons in their valence shells. This in turn causes the material to act as an insulator. Silicon and germanium in their pure form are referred to as intrinsic materials. Before these materials can be used as a form of semiconductor material, they must have impurities added to them so the material can conduct an electric current. The process of adding impurities to the intrinsic material is referred to as doping. There are 2 classifications of impurities used for doping. These are trivalent and pentavalent. Trivalent elements will contain only 3 electrons in the valence shell, whereas pentavalent elements will contain 5 electrons in the valence shell. Common pentavalent impurities include such agents as arsenic, antimony, bismuth, and phosphorus. When a pentavalent impurity is added to the intrinsic material, it causes an extra electron to be generated, because when the covalent bond forms the 2 elements together, there can be only 8 electrons in the valence shell. Since the pentavalent impurities have 5 electrons and the intrinsic materials have 4 electrons, when the 2 are combined, there is an extra free electron produced. This free electron is termed a donor. Since the electron has a negative charge, the crystalline structure which was formed by the covalent bonding is called an N-type material. When a voltage is applied to the N-type material, the electrons will flow with only a small amount of energy being applied. Common trivalent impurities include such agents as aluminum, indium, gallium, and boron. Trivalent impurities contain only 3 electrons in the valence shell. This creates a vacancy or hole when the crystalline structure is formed. Since this hole can accept an electron, it is called an acceptor. Intrinsic materials which are doped with trivalent impurities are referred to as p-type semiconductor materials. When a voltage is applied to a p-type semiconductor material, the holes will flow from the positive potential to the negative potential. This is known as hole flow and is only possible in p-type semiconductor materials. We will stop now for a short review of the material covered to this point. The maximum electrons which may exist in the valence shell of any atom is 8. The valence shell of the silicon and germanium atom will contain only 4 electrons. The closer the electrons are to the nucleus, the stronger the forces are that bond them together. Since the electrons in the valence shell are furthest from the nucleus, they require the least amount of energy to become displaced from the atom. 2 distinct energy bands exist in any material. They are the valence band and the conduction band. A third band may exist which separates these energy bands. This band is termed the forbidden gap. Insulators, as you have seen, will have a wide forbidden gap. Conductors will have no forbidden gap at all. Their energy bands will actually overlap. Semiconductor materials, on the other hand, will contain a narrow forbidden gap. There are three kinds of atomic bonds: ionic, metallic, and covalent. Insulating materials are formed with ionic bonds. Conductors are formed with metallic bonds. And semiconductor materials are formed with covalent bonds. Pure silicon and germanium are referred to as intrinsic materials. Intrinsic materials must be doped with impurities to allow the material to conduct an electric current. The two basic types of impurities used for doping are trivalent and pentavalent. Trivalent impurities contain 3 electrons in their valence shell. Pentavalent impurities contain 5 electrons in their valence shell. Trivalent impurities are used to form p-type semiconductor materials. Pentavalent impurities are used to form n-type semiconductor materials. This concludes our first review. Next, we shall examine some of the more common single-junction semiconductor devices.